Let's do this sample problem involving springs. We'll start with our box pressed up against spring 1, compressing it, but it's at rest. We're just holding it there. We let go of it, and the spring pushes it, and it goes across these frictionless surfaces up the incline and compresses spring 2 to the point where it momentarily comes to rest before spring 2 would push it back down. We don't care about that. We just want to know how much is spring 2 compressed at that instant when the box momentarily comes to rest. If we're given this information and the fact that these surfaces are frictionless, find the amount that spring 2 is compressed. So you should be thinking about which lens you're going to use for this problem. When there are springs in the system, there's one thing we know for sure. Acceleration is not constant. The springs do not push on something with a constant force. The force changes linearly. So that means that probably kinematics is not the best approach. Those equations we use for kinematics are for constant acceleration. The springs are attached to the earth, and the earth is going to get in the way and make it difficult to use momentum, because the earth, we would have to know how much the earth moved as the mass moved away from spring 1, and the earth's not going to move, so we really can't use momentum when the earth gets in the way. Energy seems like a good approach. Whenever we have springs in our system, energy tends to be one of our go-to methods for solving the problem. And because our surfaces are frictionless, we can say the mechanical energy at the beginning of the problem and the mechanical energy at the end of the problem is the same. Now we would also want to include the earth and both springs in our system. The reason we include them in the system is so we can use potential energy. Potential energy is how we account for transfers of energy within our system. If the earth is not part of our system, we cannot use gravitational potential energy. We have to say an external force of gravity is reaching into our system, doing work on our system. And if the springs are not part of our system, we can't use spring potential energy. We have to say as an external force reaching into our system, acting on our block from the springs. Most people find it easier to use potential energy. At the beginning of our problem, what types of mechanical energy could we have? We could have kinetic energy, the object could be moving. We could have energy stored in the spring, and we could have gravitational potential energy. And at the end of our problem, we could have the same three things. Let's look at each one of those. Is the mass moving at the beginning of the problem? No, it's not. So there's not going to be any kinetic energy. Is it moving at the end of the problem? No, it's not. So we can say the kinetic energy is 0 there also. At the beginning of the problem and the end of the problem, there's a different height. The box has changed altitude, right? That has gone up, higher up in the gravitational field. So its gravitational potential energy has to change. So I need to define a 0 height somewhere in this problem. I can pick any place I want. I can make it the beginning of the problem. I can make it the end of the problem. I can make it somewhere in between. The two places that make the most sense are probably the beginning or the end. Or some students like to pick the lowest point in the problem, which doesn't have to be at the beginning or the end. In this case, the lowest point is at the beginning. So we could say y equals 0 there, and as we go up, it's our positive direction. That means that at the beginning of our problem, we have no gravitational potential energy, because gravitational potential energy is mgh, and our height is 0 at that point. We've just defined it to be 0 there. But at the end of the problem, we are going to have gravitational potential energy. Now, springs. At the beginning of the problem, we have 2 springs. And at the end of the problem, we have 2 springs. At the beginning of the problem, spring 2 is not stretched or compressed. It has no energy stored in it, so its potential energy is 0. And at the end of the problem, spring 1 is not stretched or compressed, so it has 0 energy stored in it. But at the beginning of the problem, spring 1 is compressed, so it's going to have energy stored in it. So all the energy at the beginning of the problem, all the energy is stored in spring 1 in the form of spring potential energy. Spring 1's spring constant multiplied by the amount that it's compressed squared. That's a sub 1. 1/2 kx squared. And that's for spring 1, so it's spring 1's spring constant, k, and it's the amount that spring 1 was compressed. And it doesn't matter whether a spring is stretched or compressed. Either way, it has energy stored, and that energy always positive. U spring always positive. And at the end, spring 2 is compressed, and it's going to have energy stored in it. 1/2 k2 x2 squared, the spring constant for spring 2, and the amount that spring 2 is compressed. Now, all of these things are knowns except for the amount that spring 2 is compressed. Plug in everything we know, solve for delta x2.